sklearnutilsextmathrandomizedsvd. Description: a randomized algorithm for computing the singular value decomposition SVD of a matrix. This algorithm is faster than the standard SVD algorithm for large matrices, especially when only a few singular values and vectors are needed. Inputs: X, the input matrix for which the SVD is to be computed. N components, the number of singular values and vectors to compute. If none, all singular values and vectors are computed. November samples, the number of extra singular values and vectors to compute to improve the accuracy of the algorithm. Nitter, the number of iterations to perform in the randomized SVD algorithm. Outputs: U, the left singular vectors of the matrix X. S, the singular values of the matrix X. V, the right singular vectors of the matrix X. Steps: generate a random matrix with dimensions n components. November samples. X. Shape 1. Multiply the random matrix by the input matrix X. Compute the QR decomposition of the product. Compute the SVD of the R matrix from the QR decomposition. Select the top n components singular values and vectors from the SVD of R. Project the original input matrix X onto the selected singular vectors to obtain the left singular vectors U. Metrics: accuracy. The accuracy of the computed SVD can be measured by comparing the computed singular values and vectors to the results of the standard SVD algorithm. Visualization plots: singular value spectrum. A plot of the singular values in descending order can be used to visualize the distribution of the singular values. Scatter plot of the left and right singular vectors. A scatter plot of the left and right singular vectors can be used to visualize the relationship between the singular vectors. Fine-tune parameters: n components. This parameter controls the number of singular values and vectors to compute. Increasing this parameter will improve the accuracy of the algorithm, but it will also increase the computation time. November samples. This parameter controls the number of extra singular values and vectors to compute. Increasing this parameter will improve the accuracy of the algorithm, but it will also increase the computation time. Uncertainty methods: bootstrap. The bootstrap method can be used to estimate the uncertainty in the computed singular values and vectors. Challenges and fixes. Challenge 1: the randomized SVD algorithm can be sensitive to the choice of the random matrix. Sample use case that resulted in challenge 1: using a random matrix with a poor distribution of singular values can lead to inaccurate results. Fixes to challenge 1: using a random matrix with a more uniform distribution of singular values can help to improve the accuracy of the algorithm. Challenge 2: the randomized SVD algorithm can be computationally expensive for very large matrices. Sample use case that resulted in challenge 2: computing the SVD of a matrix with millions of rows and columns can take a long time. Fixes to challenge 2: using a distributed computing framework, such as Apache Spark, can help to speed up the computation.